You've been told the speed of light is the ultimate fast, but on the scale of the universe, it's a cage. That cosmic speed limit doesn't just keep your rocket slow, it locks your messages, your future, and almost the entire cosmos permanently out of reach. In this video, we're going to tear that open and see why the speed of light is less a superpower and more a prison you can never escape. But before we continue, please subscribe to the channel to give your support. Let's continue. In 1 second, light can go around Earth more than 7 times because Earth's equator is roughly 40,000 kilometers, about 25,000 miles around. So in the time you snap your fingers, light has already lapped the planet again and again. That sounds unbeatable, almost magical. But notice the comparison hiding in your head. You're secretly comparing it to a car at 100 kilometers an hour or 60 miles an hour, or a plane at around 900 kilometers an hour, 560 miles an hour. On that tiny scale, yes, light looks like a cheat code. So the first correction is simple. Your sense of fast is not wrong, it's just built on a very small sandbox. The speed of light is only godlike when you never look beyond that sandbox. The moment you zoom out, the number that looked huge starts to feel weak. Now ask yourself this. If light is really that fast, why does it already feel slow when you compare it to something as boring as your commute? Take something ordinary, a 20-kilometer daily trip, about 12 miles. Maybe that's half an hour of stop-and-go traffic for you. Light blasts through that distance in about 67 millionths of a second. Not a tenth of a second, not a hundredth, a tiny slice of a thousandth. If you tried to time that on a normal stopwatch, it would just read 0. That's how much faster light is than your normal world. Look at a big passenger jet, cruising at around 900 kilometers per hour, roughly 560 miles per hour. To your senses, that's wild. You sit in a seat and entire countries move under you in a few hours. But as a fraction of light speed, that jet is crawling. Its speed is way less than 1/100th of 1% of light speed. On any cosmic scale, that plane is basically frozen in place while light does circles around it. So on human scales, everything is painfully slow, and light is the only thing that looks remotely quick. But you don't live in a universe built for road trips and flight paths. You live inside a galaxy. So the next question is obvious. If light crushes your commute, why does it start failing as soon as you step out into the solar system? Look at just our local distances. The moon is about 384,000 kilometers away, around 239,000 miles. Light covers that in about 1.3 seconds. That means when you see the moon, you never see it as it is now, only as it was more than a second ago. Not a huge delay, but the lie is already there. The sun is about 150 million kilometers away, about 93 million miles. Light needs around 8 minutes and 20 seconds to cross that gap. So when you look at the sun, you are seeing it as it was 8 minutes ago. If the sun could instantly disappear, which it can't, you would still sit here in bright daylight for over 8 minutes because the last photons are still in transit. The now you think you see is always in the past. Push a bit farther. When we send a signal to a spacecraft near Mars at around 400 million kilometers, about 250 million miles, the one-way delay can go beyond 20 minutes. You send the command, the probe hears it 20 minutes later, it responds, and you wait another 20 minutes for the reply. 40 minutes for one back and forth. That is with signals moving at light speed, inside our own solar system, which is tiny compared to the galaxy. So by the time you get to the edge of your own backyard, instant is already gone. Lag dominates everything. If it's this bad for one star and a few planets, what happens when you scale up to the entire Milky Way? Now the numbers start to crush that light is insanely fast feeling. The Milky Way is about 100,000 light years across. 1 light year is the distance light travels in a year, roughly 9.5 trillion kilometers, around 5.9 trillion miles. So if a photon starts at one edge of the galaxy and heads straight to the other side, it needs a full 100,000 years to arrive. Think about human history for a second. Modern humans have only been around for maybe a few 100,000 years. Civilization with cities and writing is only on the order of 10,000 years. One crossing of the galaxy at light speed is 10 times longer than all recorded human history. That's how slow the fastest thing in the universe really is, once you stop thinking in terms of highways and start thinking in terms of galaxies. We usually talk about light as if it could tie a galaxy together, as if signals at that speed make things connected. But if one end of your galaxy sends a light pulse, no one at the other end will receive it for 100,000 years. By the time the message arrives, entire star systems could have formed, evolved, and died. Light is not stitching your galaxy into one unit. It is barely managing to move news from one side to the other before everything changes. And if that is the situation just for your home galaxy with 100 billion stars or so, what happens when you pull the camera all the way back and look at the full observable universe? The observable universe is the region from which light has had time to reach us since the Big Bang. Right now, its radius is about 46 billion light years. That number already tells you something brutal. Even if you could ride a light beam at full speed, you would need 46 billion years to go from here to that current edge. The universe itself is about 13.8 billion years old. So a one-way trip at light speed to the edge of what you can see would take more than 3 times the age of the universe so far. And it gets worse. While you travel, the universe is expanding. Space itself is stretching. The edge you're chasing is not fixed in place. By the time you reach where it used to be, it has moved farther away. You can never catch the moving frontier. Light speed is just not too slow to cross the universe. It's too slow to even keep up with the growth of what is visible. So line up the facts. On human scales, light feels instant. On solar system scales, it already introduces annoying delays. On galactic scales, it crawls compared to the distances involved. On the scale of the universe, it completely fails to connect one side to the other before everything changes again. The speed you were taught to think of as the ultimate fast is just not enough. Here's the real twist that sets up everything that comes next. This same not actually fast speed is also the absolute speed limit for any signal, any ship, any cause and effect. If light itself is too slow for the universe it lives in, what does it mean when you learn that nothing can ever go faster than that? How do you break a speed limit that isn't written on a sign but burned into the way reality itself works? The answer is simple. You don't. In Einstein's relativity, the speed of light in a vacuum is not just how fast light usually travels, it's the maximum speed at which any cause can affect any effect, anywhere, ever. That number, about 300,000 kilometers per second, roughly 186,000 miles per second, is the hard ceiling. No chunk of matter, no pulse of energy, no message can go faster than that by even the tiniest amount. Not by 1%, not by 1/1,000,000th of a percent, not by one atom's width per century. There is no wiggle room. And this is the key detail people miss. This is not about our engines being bad. It is not about we just haven't built the right drive yet. This is not a hardware problem. It is geometry. The equations that describe space and time themselves lock in that limit. When you boost something, you're not just changing its speed, you're changing how it moves through time and space together. And that structure simply does not allow a signal to outrun light. Trying to beat it is like trying to draw a triangle whose angles don't add up the way geometry says they must. It's not hard, it's impossible by definition. So of course, we tried anyway. If the universe says nothing can reach light speed, we build machines specifically to push particles as close as we can get, and then we watch what happens. That's what happens in particle accelerators, like the Large Hadron Collider near Geneva, a 27-kilometer-long ring buried under the ground, about 17 miles. In that ring, we whip protons around to more than 99.9999999% of light speed. That is not an exaggeration. That is literally how many nines are in the number. Here's what's interesting. When you keep adding energy to those protons, they do speed up, but not the way you expect. At lower speeds, more energy means clearly more speed. At these extreme speeds, more and more of the energy goes into something else. Their effective inertia grows, their resistance to further acceleration. Their internal clock, from our point of view, runs slower and slower. They become heavier in the sense that it gets harder and harder to change their motion. Their actual speed creeps closer to light speed, but in tiny, diminishing steps. You can pour in staggering amounts of power, and you never get faster than light. You only get a bit more almost light speed. So you can ask the obvious question here. Maybe we're just not trying hard enough. Maybe we just need more energy, a bigger collider, a better power source, and we'll finally punch through that last little gap. This is where the math turns from difficult to no chance. As something with mass approaches light speed, the energy you need to go even slightly faster shoots up. Each small increase in speed costs more energy than the last one. Early on, that's fine, you can pay it. Closer to the limit, the bill explodes. In the language physicists use, the energy required grows without bound as your speed gets closer to the speed of light. In plain language, the closer you get, the more ridiculous the energy price tag becomes. And trying to actually hit light speed exactly would require infinite energy. Infinite is not very big. Infinite is never going to happen. Put a picture on that. Take a mountain with a mass of 1 trillion tons. If you could somehow convert that entire mountain into pure energy using the famous idea that energy equals mass times the square of the speed of light, you'd get an absurd amount of energy, far beyond anything humanity will ever control. And even with that, you still would not have enough to push a decent-sized spaceship or any other massive object all the way to true light speed. You'd just buy yourself a bit closer, a slightly slimmer gap, and the wall would still be in front of you. You could say, okay, that's theory and engineering. Does nature itself actually play by these rules? It does. That's where particles like muons come in, and they give us one of the cleanest, most brutal proofs that the brick wall is real. Muons are like heavy cousins of electrons. At rest, a muon lives for about 2/millionths of a second. That is its lifetime before it decays into other particles. If a muon were moving slowly, in those 2 microseconds, it would only travel a few hundred meters at most, a short distance. But we routinely see muons created high in Earth's atmosphere by cosmic rays, tens of kilometers up, and we detect them down at the surface. On paper, that should not happen if time flowed the same for them as it does for us. They shouldn't live long enough to reach the ground. The way we reconcile this is pure relativity. From our frame, those muons are moving so close to the speed of light that their internal clocks are slowed down. Their 2 microseconds stretch out in our time. They get enough time, from our point of view, to travel tens of kilometers before they decay. In accelerators, we do the same thing. We push muons and other particles to near light speed. We measure how long they last and how far they go, and we see the same pattern every time. As you crank up their energy, their speed approaches light speed but flattens out. It refuses to cross the line. Their time dilation grows, their effective inertia grows, but the speed never punches through. Every collider, every cosmic ray shower, every lab test gives the same verdict. The brick wall at light speed is solid. So you have theory, built from the geometry of space-time, saying no faster than this. You have engineering trying to cheat with the most extreme machines we can build, failing to break it. You have natural high-energy particles hurtling through space for billions of years, still obeying it. The evidence is not one experiment, it is everything. That brings up the last and most important part of this section. If nothing can outrun light, why call that a prison and not just an interesting rule? The answer has to do with how big the universe is and how that size interacts with this fixed limit. Right now, as you sit here, there's a kind of invisible sphere around you. It's not made of material, it's defined by what you can possibly affect. Every second, that sphere grows outward at the speed of light. Light signals, radio waves, gravity changes, anything you do can only spread inside that expanding bubble. Anything inside that bubble could in principle be influenced by something you did in the past. Anything outside it has never heard of you and will not until that bubble reaches it, if it ever does. The problem is scale. The universe is not a few light seconds across, it's tens of billions of light years, and it's expanding. Your sphere of influence grows at light speed, but the arena it is trying to cover is enormous and getting bigger. On small scales, that's not a big deal. On cosmic scales, it means the region you can ever touch is a tiny, tiny fraction of everything that exists. Most of the universe is outside your future influence forever. So the cosmic speed limit is not just a number, it is a moving boundary, always expanding, but always too slow to enclose more than a small piece of reality. You are trapped inside that boundary, along with everything you care about. No technology, no clever hack, no quantum trick is going to let you spread influence faster than that shell. That is why the speed limit feels like a prison, not just a fact from a textbook. And here's the next twist this sets up. If getting close to light speed changes how time flows for you, trying to approach that wall is not just about distance, it is about what happens to your future. What happens to your own timeline when you push up against the limit that nothing can cross? How do you go faster if every step toward light speed steals time from your own future? That's the twist that makes the speed limit feel much worse. Distance you can sort of accept, but when the cost is your own years, the whole game changes. Say you actually pull off something close to science fiction. You build a ship that can cruise at 99% of light speed, about 297,000 kilometers per second, around 184,000 miles per second. You pick a target star 50 light years away. From Earth's point of view, the math is boring and brutal. Even with smart acceleration and braking, the trip still takes roughly 50 years one way, because nothing you do changes the fact that light itself needs 50 years for that distance. On board the ship, though, your story's different. As you push that close to light speed, time dilation kicks in hard. Your own clock, your heartbeat, your aging, all slow down compared to clocks back on Earth. For the people watching from home, you're gone for 50 years. For you, the clock might show 7 or 8 years. You leave in your 20s, you step out at that star still in your 30s, and everyone watching from Earth is in their 70s. So here's the question. Does that feel like a win or a trap? You've beaten the clock on board, but you've only done it by letting everyone else's clock run away from you. That's the core of the famous twin paradox, and it's not really a paradox at all, it's just uncomfortable. One twin stays on Earth, living a normal life. The other straps into a near light speed ship, goes out for a round trip, and comes back younger. That's been calculated, modeled, and confirmed in principle by many experiments on smaller scales. It looks like a cheat code for time. Travel fast enough, and you jump into the future. But the catch is absolute. You can only jump forward in other people's timeline, never backward. There is no going home to before. If you do a long enough near light speed loop, you can come back to an Earth that's decades, centuries, or even millennia older than when you left. Your friends are gone, your culture is gone, your language may be a museum piece. You can't send a warning back to the version of Earth you left. You can't fix anything that happened while you were away. The speed of light doesn't free you from history, it lets you skip chunks of it. And that's a very different thing. You might think, okay, that's cool theory and sci-fi setup, but not my problem. Except you already live in a world where we have to correct for this on a daily basis, or your phone map stops working. Time dilation isn't just a story, it's in the hardware. Look at GPS. Those satellites are orbiting about 20,000 kilometers above Earth's surface, roughly 12,000 miles up, moving at around 14,000 kilometers per hour, about 8,700 miles per hour. Two relativistic effects hit them at once. Because they're higher up, they feel slightly weaker gravity than you do on the ground, which makes their clocks tick a bit faster. Because they're moving quickly, special relativity makes their clocks tick a bit slower. When you combine both, the net effect is that their onboard clocks run about 38 billionths of a second faster per day than clocks on Earth. 38 billionths of a second sounds tiny, basically nothing, but GPS works by timing how long signals take to reach you from multiple satellites. If those clocks are off and you don't correct for it, your calculated position drifts by kilometers per day. Your navigation app would show you driving through rivers and buildings. The system only works because engineers build Einstein's relativity into the software. That's how real this is. Your phone quietly proves that time dilation is a measured effect, not a classroom curiosity. So speed doesn't just cost fuel, it distorts time. And that leads to the next layer of the prison. Distance is one wall, time is another. The faster you go, the more your own timeline peels away from everyone else's. Push the thought experiment harder. Take a galaxy 100 million light years away. You somehow get a ship that can cruise at a hair under light speed and head there. From your point of view, with extreme time dilation, maybe that journey feels like a few decades, a long but survivable career. You live through it, you see another galaxy up close. But back on Earth, 100 million years go by. Continents have moved, species have appeared and gone extinct, the sun itself has inched along its life cycle. The version of the universe you left behind is ancient history. This is the second wall. Even if you can technically reach some far-off place, you can only ever see and interact with the version of the universe that exists along your distorted time path. You were locked into a particular slice of when, just as hard as you were locked into a particular region of where. You don't just fight distance, you fight a permanent mismatch between your time and everyone else's. So here's the really sharp edge. Going faster feels like it should give you more universe, more places, more experiences. Relativity flips that. The closer you get to light speed, the more you pay in energy and the more you detach your personal time from the timeline of the things you care about. You can leave home, you can cross vast distances on your own clock, but the cost is that when you arrive, your home has moved on without you, maybe completely beyond recognition. So in that sense, the faster you go, the less you actually get. You burn staggering amounts of fuel or whatever advanced propulsion you have, you deal with insane engineering problems, you accept massive radiation risks, and the payoff is a universe that you can see but not really stay connected to. You can surf the edge of light speed, but the story you return to, if you ever return, is one you can no longer influence in any meaningful way. So now you have two walls. A speed limit that locks how quickly causes can spread, and a time distortion that punishes you for approaching that limit. But there's an even stricter structure hiding underneath both, a map that tells you in a very cold way which events in the universe you can ever touch at all, no matter how fast you go or how early you start. There are parts of the universe that might as well not exist for you. Not now, not ever. Not because they're far away in some vague sense, but because the rules of space-time literally cut them out of your story. That's what light cones actually say, and it's a lot harsher than the way they're usually drawn in textbooks. In relativity, every here and now is an event, a single point in four-dimensional space-time, 3 directions of space plus 1 of time. Take your current moment, you sitting wherever you are. From that point, you can ask a very clear question. Where can light go from here, and where could light have come from to reach here? All the possible paths a light signal could take outward into the future in all directions form what's called your future light cone. It's the set of events that, in principle, can still be influenced by something you do right now, because a light speed signal has time to reach them. Flip the direction, and all the paths light could have taken to get to you from the past form your past light cone. That's the set of events that, in principle, could have already affected you. Everything outside those two regions is given a very cold name, elsewhere. Elsewhere is not just far away. Elsewhere means completely disconnected from you in terms of cause and effect at this moment. No signal from those events has had time to reach you yet, and no signal you send now can reach them yet. Right now, they're off the board. So here's the tension. You live your life thinking you're in one big connected universe, but space-time is carving that universe into reachable, has reached, and never touched you in a very strict way. Put some numbers on this, because hand-waving doesn't show how brutal it is. Take a galaxy 10 billion light-years away. Light from that galaxy takes 10 billion years on the best possible path to get here. If photons from a supernova in that galaxy hit your telescope today, that explosion did not just happen. It happened 10 billion years ago. Only now does that event enter your past light cone. Before this moment, that supernova literally might as well not have existed for you. It was real, it happened, but it wasn't in the set of events that could possibly have affected you. Now flip it around. You fire a laser toward that same galaxy today, a tight beam, perfectly aimed. In the absolute best case, That signal arrives there 10 billion years from now. Any response from whatever is out there can only come back another 10 billion years after that. You're looking at a 20 billion year round trip just to say hello and hear hi back. On human timescales, that isn't communication, that's geological drift. So now ask, what about things that are happening out there right now, in that galaxy, at this same moment in some reasonable definition? That's where the elsewhere region becomes very real. The distance is so huge that any event happening there right now is outside both your past light cone and your future light cone as of this instant. It hasn't had time to send you any signal, and you haven't had time to send it anything it could receive yet. That means right now, that explosion, that orbit, that civilization, whatever is going on there, is mutually irrelevant with you. You can't know about it yet, and nothing you do right now can influence it yet. At this instant, there is no possible causal link between you and that event. It lives in the elsewhere zone. And here's the uncomfortable part. That's not a rare exception. For almost every event in the universe relative to you right now, the relationship is elsewhere. The set of events that can affect you or be affected by you is a tiny slice compared to everything that exists. The grid of space-time is mostly off-limits. Physicists don't just wave their hands about this and say, trust us. They formalize it in what's called Minkowski spacetime, the mathematical framework for special relativity. In that language, the separation between two events can be one of three types. Time-like means one event can cause the other with a signal slower than or equal to light. Light-like means they're exactly on the path a light signal could take. Space-like means they're too far apart in space for any signal to get from one to the other in time, so they cannot be causally connected. All the events inside your light cones are time-like or light-like separated from your current moment. Everything in the elsewhere region is space-like separated. No cause and effect link, period. That's not philosophy, that's classification. And this is where experiments matter. In particle physics, every collision, every decay, every detector click has to respect this structure. We set up beams of particles. We know where and when they hit targets. We measure the showers of new particles and their arrival times in detectors. If any signal, any particle, could jump outside its allowed light cone, we would see cause and effect out of order, or we'd see something arriving earlier than any light speed signal could take. After decades of high-energy experiments, nothing does that. The timing, the positions, the correlations all line up with the rule. No influence leaks outside the light cone. So the light cone picture is not just a pretty diagram you draw once and forget. It is baked into how the universe actually behaves at the most fundamental high-precision level we can test. Now, zoom back out from math to your own life. As you move forward in time, second by second, your past light cone grows. More of the universe's history, more distant events, have had enough time to send light or other signals to reach you. A galaxy that was once elsewhere eventually drops into your past light cone when its light finally arrives. In that sense, your knowable universe gets bigger. But here comes the next layer of the prison. The universe is expanding, and that expansion is not slowing down, it's accelerating. That means that while your past light cone keeps pulling more of the ancient universe into view, your future light cone is losing ground against the growth of space. There are regions of space that are being pulled away from you so fast by cosmic expansion that no signal you send, even at light speed, will ever reach them. They will never enter your future light cone. They are causally disconnected from you forever. So as time passes, there is this weird split. The part of the past you can, in principle, learn about increases, but the fraction of the future you can, in principle, affect shrinks in a relative sense. More and more of the universe's future lies permanently outside your reach. Those regions will have their own light cones, their own local stories, but you will never be part of them. When you put all of this together, the picture is very stark. The speed of light does not just limit how fast you can travel from point A to point B, it defines the shape of your reachable spacetime, the bubble of events that can ever matter to you or be changed by you. Most of spacetime, in a precise mathematical sense, is locked behind those light cone walls. And if that's already true just from the structure of relativity, what happens when you add on the extra fact that the universe itself is stretching so fast that entire galaxies are already gone for good? Not in some poetic way, in a hard, numbers-on-paper way. The combination of light speed and expansion means they're already outside anything you could ever reach, no matter how long you wait or how advanced your technology gets. On the largest scales, galaxies aren't just sitting there, they're receding from us, and the farther away they are, the faster they recede. That pattern is Hubble's law. For every megaparsec of distance, that's about 3.26 million light-years, the recession speed increases by about 70 kilometers per second, roughly 43 miles per second. So a galaxy 1 megaparsec away is drifting at 70 kilometers per second. Keep scaling up, and by the time you get to around 4,300 megaparsecs, over 14 billion light-years, the recession speed hits roughly the speed of light. So just from that simple rule, distance times about 70, you already see something crazy. Push far enough out, and the math says those galaxies are moving away from us faster than light. At first glance, that sounds like a direct violation of everything we just said about the cosmic speed limit. If nothing can outrun light, how can entire galaxies be receding us at or above light speed? The key is that those galaxies aren't flying through space like bullets breaking the limit. Space itself is stretching, and the galaxies are basically stuck in that fabric. Locally, in any small region, Einstein's rule still holds. No object, no signal can move through space faster than light. Your ship, your radio pulse, your particle beam all obey that limit. But when you zoom out over billions of light years, you're no longer dealing with motion through space, you're dealing with the metric of space itself changing. Think of it this way. Not as an analogy, but as a clear distinction. There's local motion and there's global expansion. Locally, your speed relative to nearby stuff is always sublight. Globally, the distance between two far apart points can grow so fast because the underlying grid is stretching that the separation increases by more than 300,000 kilometers every second. A photon trying to go one way is chasing a moving target, and beyond some distance, the target is running away faster than any photon can close the gap. So once you accept that, the next question is unavoidable. If expansion can outrun light, is there a hard boundary where anything beyond that is lost to us forever? That's where the idea of a cosmic horizon comes in. There is some distance, on the order of tens of billions of light years, beyond which any light you send today will never, ever arrive. Not in your lifetime, not before stars burn out, literally never. The reason is that the universe is not just expanding, it's accelerating, driven by what we call dark energy. That acceleration keeps pulling those regions away so fast that your light signal gets stretched and dragged and effectively frozen, never quite getting there. The confusing part is that this horizon distance is larger than the simple age of the universe times speed of light number. Light has only had about 13.8 billion years to travel, but because space has stretched while light was on the way, the current radius of the observable universe is about 46 billion light years. The horizon, the boundary for signals you send now, is also out at tens of billions of light years. Anything beyond that, if you aim a photon at it today, is gone in principle. It will never receive what you're sending. This isn't just guessed, it comes straight from observations. In the late 1990s, two teams of astronomers were studying special exploding stars called Type 1a supernovae in very distant galaxies. These supernovae have roughly known intrinsic brightness, so they act like standard candles. If you know how bright something really is, and you see how faint it looks, you can work out how far away it is. When they did the measurements, they found those supernovae were dimmer than they would be in a universe where expansion was slowing down under gravity alone. Dimmer meant farther than expected. The only consistent way to explain that was that the universe's expansion had sped up over time, not slowed down. That discovery is where the modern picture of dark energy comes from. Some form of energy built into space itself, with a kind of negative pressure that drives acceleration. Whatever its deep nature, the effect is clear. The scale factor of the universe grows faster and faster, and distant galaxies accelerate away. A causal sense, it's moving inward, because a set of places you could one day reach with a light speed signal is shrinking as a fraction of everything that exists. So what does that do to the long-term picture? Fast forward tens of billions of years, or even hundreds of billions. Right now, we see galaxies out to huge distances, and we can map a cosmic web of clusters and filaments. But as expansion and redshift continue, the light from most of those galaxies gets stretched to longer and longer wavelengths. Visible light shifts to infrared, then microwave, then to radio waves with wavelengths so long and intensity so low that no realistic telescope can detect them. They fade out of practical existence. Future observers living in whatever the Milky Way and Andromeda and our small neighbors have merged into will look up and see a mostly dark sky. They'll have a huge galaxy or merged cluster of stars, maybe a few leftover nearby dwarf galaxies. And that's it. No obvious cosmic web, no dense background of galaxies, no clear Hubble expansion in their surveys. Without deep theoretical work and extremely careful relic measurements, they might have no direct evidence that there was ever a hot Big Bang, or an expanding universe or other island galaxies at all. So the combination is brutal. The speed of light fixes how fast influence can spread. Dark energy makes the arena grow faster and faster. Together, they don't just make intergalactic travel hard, they make most of it fundamentally impossible. And in the long run, they erase almost all visible traces that a larger universe ever existed. The natural endpoint is not a crowded, buzzing cosmos. It's a set of isolated island universes, each cut off from the rest by horizons that no signal can cross. And even before that bleak future arrives, there's another layer of the trap already in play right now. Even within the tiny patch of sky you still can see, you never see anything as it is now. Every photon that hits your eyes or your telescope is old news, delayed by that same speed limit that's blocking everything else. You never see the universe as it is, only as it was, not just for faraway galaxies, but for everything, all the time. The speed of light builds a permanent delay into every signal that ever reaches your eyes or your instruments, so your now is always a lie. Start close to home. When you look at the sun, you're seeing it as it was about 8 minutes ago, because light needs around 8 minutes and 20 seconds to cross the 150 million kilometers, about 93 million miles, between Earth and the sun. If something dramatic happened there right this second, you would only find out more than 8 minutes later. For those 8 minutes, your sky would be wrong, and there is nothing you could do about it. The nearest star system, Proxima Centauri, is a bit over 4 light years away. A light year is the distance light travels in 1 year, so that system is more than 4 years of light travel away, over 40 trillion kilometers, around 25 trillion miles. When you see that star, you see it as it was 4 years ago. If it vanished yesterday, your telescopes would still show a perfectly normal star, because yesterday's light hasn't even started to be a problem. You're still watching photons that left 4 years back. Now, push to Andromeda, the nearest large galaxy. It's about 2.5 million light years away. Light from no stars left when early humans didn't exist yet. Every time you see a picture of Andromeda, you are looking at a frame from a universe where there were no modern humans on Earth. There is no such thing as a live, real-time view of any of this. The entire sky is delayed footage. So the natural question is, how bad does that delay get when you stop talking about millions of years and start talking about billions? When telescopes like Hubble or the James Webb Telescope stare deep into the sky, they collect light from galaxies so far away that the photons have been traveling for 10 to 13 billion years. The universe is about 13.8 billion years old, which means some of those galaxies are being seen when they were very young, only a few 100 million years after the Big Bang. In those images, you're looking at crowded, chaotic baby galaxies, still assembling their stars and structure. There is no way to know what those galaxies look like right now in the present moment. To get an updated snapshot, you'd have to wait another 10 to 13 billion years for new light to arrive, while the universe continues to expand and evolve. By the time any of that fresh light reaches us, entire galaxies could have merged, been stripped, or faded. The objects in those deep field images are not out there in that state anymore. You are looking at fossil frames from an ancient version of the universe. If that's true for galaxies, what about the oldest light we can see at all? The thing that sits behind every other image, coming from every direction. That's the cosmic microwave background. It's radiation left over from when the universe was only about 380,000 years old. At that time, the universe was a hot, dense plasma of protons, electrons, and photons. Light could not travel far without bouncing off charged particles. The whole thing was opaque. As it expanded and cooled, protons and electrons combined into neutral atoms, and suddenly space became transparent. At that moment, light was finally free to move in straight lines. That first free light has been traveling ever since, stretched and thinned out by the expansion of space. We detect it today as a faint microwave glow that fills the whole sky, with a temperature of only a few degrees above absolute zero. It is literally a snapshot of the universe when it was a baby, long before any stars or galaxies existed. There is nothing newer behind it, because before that moment, light simply couldn't get through the fog to travel. So you have this entire hierarchy of delays: minutes for the sun, years for nearby stars, millions for local galaxies, billions for deep fields, and almost the entire age of the universe for the microwave background. One question remains: why does the light get weaker and redder as it travels? And what does that have to do with your prism? As the universe expands, the distance between any two far apart points grows. Photons moving through that expanding space get stretched along with it. Their wavelength increase, which means their color shifts toward the red, and then beyond. Light that started as high-energy ultraviolet or even higher energy in some early galaxy can arrive here billions of years later as faint infrared, almost invisible to the human eye, or even longer wavelength radiation. The farther away the source, the more time the photon spends writing that expansion, and the more its wavelength is stretched. That stretching is what we call redshift. For modest distances, it just nudges light toward the red end of the visible spectrum. For extreme distances, it pushes light completely out of the visible band and into infrared, microwave, or radio waves, with wavelengths so long and intensity so low that no realistic telescope can detect them. They fade out of practical existence. So your live universe is built out of two layers of distortion at once: time delay and wavelength stretch. Every photon that hits your retina or your detector is old, and it's been modified by billions of years of expansion on the way in. Every observation you make is constructed from these delayed, stretched signals. The sun in the sky is 8 minutes in the past. The nearest stars are years in the past. Andromeda is millions in the past. A quasar 12 billion light years away is 12 billion years in the past, and for all you know, that object shut down long ago, or merged or transformed into something unrecognizable. You will never get the update. Your brain wants to believe that when you look out, you see some kind of present tense universe, a real-time environment you exist inside. The physics says no. What you actually see is a time-layered fossil, a stack of old signals, each one arriving with its own built-in delay and redshift. There's no way around that, because the same speed limit that stops you from reaching distant galaxies also controls how quickly their light can reach you. If light is already too slow to show you the real-time state of the universe, what happens in places where light can't escape at all, where the escape speed itself hits the speed of light and then goes beyond it? What does now even mean in a region where not even photons can carry information back out? What happens when the speed of light, the thing that's supposed to be your escape route, actually becomes the lock on the door? That's what a black hole is. Not just a strong gravity well, but a place where the escape speed and the light speed limit slam into each other and turn into a local jail. Start with something familiar: escape velocity. To leave Earth forever, never fall back, you need to hit about 11.2 kilometers per second, roughly 25,000 miles per hour. If your rocket leaves slower than that, gravity eventually drags it back. Go faster than that, and you're gone. From the sun's surface, the required escape speed is way higher, around 617 kilometers per second, about 383,000 miles per hour. Stronger gravity, higher escape speed. A black hole is what you get when you cram enough mass into a small enough volume that, at some radius, the escape speed required hits 300,000 kilometers per second, about 186,000 miles per second, the speed of light. Below that radius, any path that tries to get out would need to outrun light itself, and that is forbidden. Above that radius, escape is hard but possible. At that radius and inwards, escape is impossible, not because your engines are bad, but because physics says no signal can be that fast. So the first key point is simple. A black hole is not magic. It's just gravity plus the same speed limit we've been talking about, pushed to the extreme where light can't win anymore. If that's the rule, the next question is, do we have actual black holes where this happens, with real numbers we can quote, and not just theory on a board? At the center of the Milky Way, there is a supermassive black hole we call Sagittarius A. Its mass is about 4 million times the mass of the Sun. When you put that mass into Einstein's gravity, you can work out the radius of the event horizon, the point where escape speed hits light speed. For Sagittarius A, that radius is around 12 million kilometers, about 7.5 million miles. That is smaller than Mercury's orbit. You're talking about a region smaller than the path of the innermost planet, holding the mass of millions of suns, all concentrated so tightly that space and time are warped to the point where not even light can get away once it gets too close. Outside that radius, stars orbit it, gas swirls around it. Everything behaves like there's an ultra-compact, ultra-massive object in the middle. Inside that radius, you don't get to find out what happens, because no signal from there can reach you. So this is not vague, it's precise. A specific mass, a specific radius, and a sharp line where the rules flip from you can escape if you're fast enough to you can't escape at all. That leads straight to the really uncomfortable part. What does that sharp line, the event horizon, actually mean for information, messages, and anything that crosses it? The event horizon is that boundary where all possible paths for light and matter tilt inward. If you are outside it, you can, in principle, fire your rockets, aim outward, and if you're powerful enough, you can climb away. If you are just inside it, you can still move, you can still fire rockets, but every possible path you can choose, even the ones that feel like up, still end up deeper inside. There is no trajectory, no clever curve that takes you back out across that horizon. From the outside, anything falling toward the event horizon appears to slow down. Its clock runs slower and slower due to gravity, and its light gets stretched to redder and redder wavelengths. It fades and freezes, apparently hovering at the edge. But that's just your view, sitting far away in weaker gravity. From the point of view of the falling object, it crosses the horizon in a finite time and keeps going in. The key fact is this: no matter what it does next, no signal it sends, no flash of light, no blast of radiation can ever climb back out and inform the rest of the universe what happened. So crossing that radius doesn't just mean you're stuck, it means you are scrubbed out of the outside universe's future. You stop being part of the story anyone outside can see or affect. For everything beyond the horizon, you might as well have been deleted. So that raises one obvious challenge. If nothing can escape and the interior is invisible, how do we know black holes are really there and not just some math trick? The answer is, we don't see black holes directly. We see their effects on matter outside the horizon, and those effects line up with the predictions.
Gas and dust falling toward a black hole don't go straight in cleanly. They usually form a spinning disk, an accretion disk. As that matter spirals inward, friction and magnetic fields heat it to millions of degrees. At those temperatures, it emits X-rays and sometimes even more energetic gamma rays. We detect these as bright X-ray sources in our galaxy, in systems where a normal star is feeding a compact, invisible partner, and as extremely bright cores of distant galaxies, called active nuclear galaxies, where supermassive black holes are rapidly feeding. On top of that, we've now used instruments like the Event Horizon Telescope, a worldwide network of radio dishes acting together to image the immediate surroundings of supermassive black holes. The famous images show a bright, lopsided ring of emission and a dark central shadow. That shadow's size and shape match what general relativity predicts for a black hole of the measured mass, including the role of the light speed limit in bending and trapping photons near the horizon. The dark patch is not the hole itself, but a region where light paths are so distorted that almost no photons come straight to us. The match between theory and observation is very tight. So black holes aren't just theory, they're observed systems with accretion disks, flares, jets, and shadows that all scream the same message. This is an object where light speed escape has failed. Once you accept that, you hit the next question. Do these jails ever end, or do they sit there forever, locking information away? Quantum mechanics adds a twist, called Hawking radiation. In simple terms, when you combine quantum field theory with curved spacetime, you find that black holes are not perfectly black. They slowly leak energy, as if they have a temperature, and emit a tiny amount of radiation. As they radiate, they lose mass, and over extremely long times, they can evaporate completely. That sounds like an escape route until you see the timescales. A black hole with the mass of the Sun would take around 10 to the power of 67 years to evaporate. That's a 1 followed by 67 zeros. A supermassive black hole, like the one in the center of the Milky Way, could take up to around 10 to the power of 100 years or more. Compare that to the age of the universe right now, about 13.8 billion years, which is roughly 10 to the power of 10 years. You're talking about lifetimes that are tens of billions of times longer than the current age of everything. So yes, in principle, black holes slowly leak and eventually vanish. But for any practical timeline, they are effectively eternal prisons, defined by the speed of light limit and extreme gravity working together. Once something falls in, it is gone from the outside universe's reach for longer than stars will live, longer than galaxies will shine, longer than almost anything else that happens. You've seen how gravity plus the light speed ceiling can carve out regions where reality is permanently hidden. But black holes are not the only extreme test of this rule. The universe itself has built natural accelerators that fling particles to energies far beyond anything humans can make, and even those fastest bullets still slam into the same invisible wall you do. So if nature itself, throwing everything it has at the problem, can't break the speed limit, what makes you think you ever will? Space is already running the most violent, high-energy experiments possible, and every single one still slams into the same ceiling you do. Start with ultra-high-energy cosmic rays. These are mostly protons and atomic nuclei that hit our atmosphere with ridiculous energies, up to around 100 quintillion electron volts. In plain terms, you take the kinetic energy of a thrown baseball and you cram it into a single proton, one particle carrying as much punch as something you can actually hold in your hand. That is not a lab setup. That is nature casually throwing microscopic bullets at near maximum power.
At those energies, these particles move at speeds so close to light speed that the difference shows up only way out in the decimal places. You could write 0 point, then a long string of nines, then some digits, and that's the factor of light speed they're at. For anything built at human scale, you would just call that light speed and move on. But when you actually calculate the velocity, it is always just a bit less than the speed of light in a vacuum. Never equal, never beyond. These particles are accelerated by things like shock waves from supernovae, magnetic fields around neutron stars, and the environments near black holes. Those are engines far more powerful and long-running than anything you will ever build. Yet, even with that kind of push, even over millions of years of travel, the result is always the same. Almost light speed, not broke the barrier. Nature's own accelerators respect the same line your colliders do. You might then look at particles that are almost massless and ask if they get a special deal. Neutrinos are the obvious test. They are ghost-like, they barely interact with matter, and their rest mass is incredibly tiny, much less than an electron's, with an upper limit less than about 1 electron volt divided by the square of light speed. In metric terms, that is absurdly small. Trillions of them from the sun pass through your body every second, and you don't feel a thing. If any particle had a chance to flirt with superluminal travel, you might expect it to be neutrinos. They stream out of nuclear reactions in stars, in reactors on Earth, and in violent cosmic events like supernovae. When supernova 1987A went off in a nearby galaxy, detectors on Earth picked up a burst of neutrinos, and then within a few hours, the visible light from the explosion arrived. The key detail is timing. If neutrinos could significantly outrun light over those distances, you'd see them arrive years or days ahead, not just hours. They didn't. They were slightly early because they're produced a bit differently in the collapsing core, but they were not far ahead messengers from a faster-than-light sector. Their speeds, once you work them out, are very close to light speed, but still under the limit. So even the ghost particles with masses near zero still obey the same rule. Close, closer, but never over. There's a common place where your intuition does get tricked into thinking something has gone faster than light, and that's where Cherenkov radiation shows up. Light in a vacuum moves at the maximum speed, but when light travels through a material like water or glass, it moves slower. In water, for example, it drops to about 3/4 of its vacuum speed. That means you can have a charged particle, like an electron, streaking through the water faster than light can move through that water, while still being slower than light in a vacuum. When that happens, the particle produces a shock wave in the electromagnetic field, and you see a blue glow, called Cherenkov radiation. It's a bit like the visual analog of a sonic boom, but again, don't lean too hard on the analogy. The key is the particle is outrunning light in that medium, not the true universal light speed limit. We use this effect in gigantic water-filled detectors buried underground to spot the rare interactions when a neutrino hits a nucleus and produces a fast charged particle. The detectors light up in rings of blue. It looks like something has gone superluminal, but when you check the numbers, the vacuum limit is still intact. The rule is not broken. Your intuition just gets fooled by the difference between light in a medium and light in empty space. If you want to see the universe testing the limit on huge scales, gamma-ray bursts are some of the most extreme cases. These are brief flashes of high-energy gamma radiation that can, in a few seconds, release as much energy as the sun will emit in 10 billion years. They are linked to things like collapsing massive stars or mergers of neutron stars. In these events, jets of matter and radiation shoot out at speeds extremely close to light speed. The stuff doing the emitting is moving so fast that time is squeezed along the jet direction, and relativistic beaming focuses the light into narrow cones. That's why if you're in the beam, the burst looks unbelievably bright. We record the arrival times of different energies of photons. We look at the structure of the burst. We compare the light curves, and everything lines up with a model where nothing in that system outruns light. The way the pulse gets stretched, the way the spectrum evolves, all of it points to motion very close to light speed, but still under. If there were signals or particles arriving ahead of the main light front by more than what standard physics predicts, we'd see it in those detailed measurements. We don't. So, from the highest energy cosmic rays to the lightest known massive particles to the most violent cosmic explosions, the universe is constantly slamming matter and radiation into the walls of the light speed limit. And every time, the pattern is the same. Approach, asymptote, never cross. The important thing is, this is all data, not just theory. Cosmic rays hitting the upper atmosphere produce particle showers, and we measure their energies in arrival directions. Neutrinos fly straight through Earth, and in rare cases, they leave tracks in massive detectors that tell us their energies and times.
Cherenkov rings show us speeds in media. Gamma-ray telescopes in space and on the ground timestamp bursts and flares down to fractions of a second. When you stack up all of that, what you get is a huge, messy, real-world experiment that has been running for billions of years across the entire universe. And the verdict, every single time, is that the speed of light in a vacuum is the ceiling for signal speed. There are no hidden exceptions popping up in some corner of parameter space. The prism bars do not bend even under the most extreme conditions nature can throw at them. So if nature, with supernovae, black holes, and gamma-ray jets as its equipment, can't get anything through that barrier, what happens when you try something much more modest, like just talking to the nearest stars? What does this same speed limit do to not just exotic particles, but to any hope of having an actual conversation with another civilization, even in your own tiny slice of the galaxy? Even your closest neighboring star is basically unreachable for anything that feels like a conversation. Not unreachable for signals at all, but unreachable for the kind of back and forth your brain calls talking, because the speed of light delay stretches every exchange into a multi-year delay. Take Proxima Centauri. It's about 4.24 light-years away, roughly 40 trillion kilometers, around 25 trillion miles. That's the closest star beyond the sun, the easy one, the right next door case. A radio signal from Earth moving at light speed takes 4.24 years to get there. If something there answers instantly, their reply takes another 4.24 years to get back. So you send a simple yes or no question today, are you there? And best case, you wait almost 9 years to hear yes or no. That's not a conversation. That's slow motion mail. You can't negotiate. You can't react quickly to anything. You can't do real-time science or anything that relies on fast feedback. The light speed delay has already broken the idea of talking to the nearest star. If that's how bad it is for the closest system, what happens when you expand the radius just a bit to include more stars, more possible civilizations, more targets? Draw a sphere around Earth with a radius of 100 light-years. That's about 950 trillion kilometers, roughly 590 trillion miles. Inside that volume, there are thousands of stars, and given what we know about exoplanets, probably tens of thousands of planets, maybe more. By galactic standards, that's your immediate neighborhood, the local bubble where things are still relatively nearby. Even at light speed, a single one-way message to the edge of that sphere takes a century. You send it now, and someone there receives it 100 years later. If they reply right away, you get the answer 200 years after you started. From your point of view, everyone out there is writing to your great-great-grandchildren, not to you. You are not talking to neighbors, you are talking to the future, and they are talking to their past. The delay is so long that any shared project, any joint decision, any live communication is impossible. So that's within 100 light-years, still a tiny patch of the Milky Way. Scale up again and ask what communication across the whole galaxy looks like. The Milky Way is roughly 100,000 light-years across. If a civilization on the far side started broadcasting a message at the exact moment humans first began using radio seriously, about a century and a half ago, their signal is still 99,850 light-years away. It will not reach us for another 100,000 years. The same goes the other way. Our oldest radio leakage has barely begun to crawl away from us. It has covered a radius of roughly 100 to 150 light-years at most. That's a tiny bubble in a galaxy of maybe 100 billion stars. Even if the galaxy is full of intelligent life, scattered all over, the windows where their active radio phases overlap with ours are tiny. A civilization could rise, broadcast for 10,000 years, then die out. Their signals might pass through regions where there is no one to receive them yet, or where the receivers are long gone. Over these distances and timescales, overlapping communication windows are rare by design. The silence we hear is not proof that nobody exists. It's partly a consequence of light speed delays and finite civilization lifetimes. If that still feels abstract, bring it down to something we actually built and control, and look at how much lag we already deal with inside our own solar system.
Voyager 1, our most distant spacecraft, is currently around 24 billion kilometers from Earth, about 15 billion miles. That's more than 160 times farther away than the distance from Earth to the Sun. When we send the radio signal to Voyager 1, it takes over 22 hours to get there, and more than 22 hours for the reply to get back. So a simple command and confirmation cycle takes almost 2 days. And this is still inside the sun's gravitational zone, still home turf, not even 1 light day away, nowhere near a light year. Now scale that delay up to interstellar distances. The pattern is obvious. Our current technologies and even optimistic future ones run on human lifetimes and human patience. Light-limited distances, even inside the galaxy, run on 100,000-year clocks. Your brain and your tools are completely mismatched to the size of the playground. This reframes a famous question, the Fermi paradox. Where is everybody? One answer is simply too far for it to matter to you. Civilizations can rise and fall, separated by thousands or tens of thousands of light years. They can build radio telescopes, send messages, even seed probes, and never have a single meaningful two-way exchange with each other before one or both vanish. Light-speed communication is just too slow on those scales, and their active windows are too short. So the speed of light doesn't just make interstellar travel hard, it kills any hope of real-time cooperation, culture, or shared projects on galactic scales. You can send messages into the dark, you can maybe get a reply ages later, but you can't build a single synchronized civilization stretched over thousands of light years. The delay crushes that idea. Up to this point, we've mostly been talking about signals, about photons carrying information. But what happens when you stop talking about messages and start talking about moving actual mass, ships, and people? If light speed delays already destroy conversation with your closest neighbors, what does the same speed limit do to rockets that are millions of times slower than light, and to any dream of physically reaching those stars instead of just shouting at them across centuries? Rockets feel powerful, but on the scale set by light, they're basically toys. The numbers look impressive on launch day, the ground shakes, the noise is brutal, but once you stack those numbers against 300,000 kilometers per second, about 186,000 miles per second, the whole idea of Starship collapses fast. Start with chemical rockets, the tech you've actually flown. The Saturn V that took humans to the moon blasted exhaust out the back at around 3 kilometers per second, about 6,700 miles per hour. The best chemical engines we've built get maybe 4.5 kilometers per second. That exhaust speed is the core of what a rocket can do. It's the leverage it has against gravity and inertia. Now compare that to light. 3 kilometers per second is 1/100,000th of light speed. That's 1/10 of 1% of 1%. It sounds like a tiny detail, but it's brutal in practice. At those speeds, even if you could magically keep burning forever and not run out of fuel, reaching the nearest star, 4.24 light years away, would take hundreds of thousands of years. That's not a mission. That's longer than your species had agriculture. So chemical rockets, even the legendary ones, are basically glorified fireworks. They're fine for hopping around your own gravity well, reaching orbit, maybe hitting nearby planets and moons. The moment you start thinking in light years, they're dead on arrival. You might respond with, fine, so chemical is trash for interstellar travel. What about advanced stuff? Nuclear, ion drives, all the next-gen ideas. The answer is better, but still nowhere near enough to change the picture. Nuclear thermal rockets, where you use a nuclear reactor to heat propellant instead of burning chemicals, could push exhaust speeds up to around 8 or 9 kilometers per second, maybe a bit more with clever design. That's about double or triple what a chemical gives you. Nice upgrade. Still microscopic next to light speed. Electric propulsion, like ion drives, goes higher. Ion engines can throw ions out the back at 30 to 50 kilometers per second, sometimes more. That's an order of magnitude better than chemical.
but they do it with extremely low thrust. You accelerate very slowly, millimeters per second squared, far less than 1 g. They're fantastic for cargo, station keeping, and long, patient missions where you don't care how long the burn takes. For crude interstellar travel on human timescales, they're still painfully weak. Even if you jump ahead and talk about aggressive near-future concepts, beaming power to light sails, fusion drives, advanced nuclear systems, and you somehow get a ship up to 10% of light speed, about 30,000 kilometers per second, roughly 18,600 miles per second, the universe still wins. At that speed, a 4-light-year trip to Proxima Centauri in a straight line, with no time spent accelerating or decelerating, takes over 40 years one way. Once you add realistic acceleration and braking phases, you're easily looking at half a century or more for a round trip, assuming everything works perfectly. So even the optimistic, fast interstellar ships we sketch on paper are nowhere close to light speed, and still demand multi-decade trips just to reach the first star next door. Short compared to cosmic time, completely incompatible with a normal human life. Underneath all of this is an energy problem that doesn't go away just because you slap advanced or fusion on the engine. The faster you want to go, the more energy you have to dump into your ship, and that cost ramps up brutally. Take a starship with a mass of 1,000,000 kilograms, 1,000 tons, roughly a small skyscraper's worth of material in space. To push that up to 1/10 of light speed, you're talking about an energy budget on the order of the entire annual energy use of human civilization, or more depending on your assumptions. That's every power plant, every reactor, every barrel of oil, every solar panel, all dedicated to speeding up one ship to just 10% of light speed. And that's still deep in the slow compared to light regime. When you start pushing toward 90% of light speed, then 99, then 99.9, the energy climb is worse than linear. Each extra 9 in how close you are to light speed costs you hugely more energy than the last one. In the relativistic regime, you're not just making the ship move faster, you're ramping up its relativistic inertia and playing with time dilation. The graph of energy versus speed curves upward, and near light speed, it's basically a vertical wall. There's another harsh piece of math sitting in the background, the rocket equation. You don't need the formula to feel what it means. The change in speed your rocket can achieve depends on two main things: how fast your exhaust comes out, and the ratio between your starting mass, ship plus fuel, and your ending mass, ship after burning that fuel. The relationship is logarithmic, which is a fancy way of saying you get diminishing returns. Double your math ratio and you don't get double your speed. You get a much smaller bump. What that means in practice is simple. If you want a modest change in speed, your rocket can be, say, half fuel and half payload in structure. If you want a huge change in speed, a significant fraction of light speed, your rocket has to be almost all fuel with a tiny payload. Push it too far and the numbers go insane. You end up with designs where the payload is a small capsule and everything else is tank. Try to hit a big fraction of light speed with chemical fuel and the rocket equation basically laughs at you. The required fuel mass becomes so enormous that it's physically meaningless. You'd need structures bigger than planets. That's not a pessimistic opinion. That's what the math gives you. This is why people dream about things like antimatter. Antimatter annihilation, in theory, lets you convert almost all of the fuel's mass into energy, far more efficient than nuclear fission or fusion, which only tap a small fraction of the mass. If you could produce and store antimatter safely, and if you could direct that energy into exhaust in a controlled way, you'd have the highest specific energy fuel you can write down in normal physics. But even then, relativity doesn't budge. As you push a ship closer and closer to light speed, more and more of the energy you pour in goes into increasing its relativistic inertia and slowing its proper time, not into increasing its speed relative to the universe by the same amount. You get closer and closer to light speed, but the last tiny sliver to reach it exactly still demands infinite energy. Antimatter makes the engineering problem insane instead of impossible, but it does not change the underlying rule. So on one side, you have light speed setting the ultimate ceiling.
On the other side, you have chemical, nuclear, ion, maybe antimatter, all hitting practical walls long before you ever reach that ceiling. The gap between what physics allows and what engineering can reach is enormous, and the gap between what physics allows and what would actually be useful for exploring a galaxy is even worse. If ships and rockets can't break you out of the prison, the next instinct is to look for a hack in the laws themselves. Quantum mechanics looks tempting because it talks about entanglement, instant correlations, spooky action at a distance. If you can't move matter faster than light, maybe you can at least move information that way and beat the delay. But when you look closely at what experiments actually show, even that door slams shut. Quantum mechanics dangles something in front of you that looks like a loophole and then slams it shut. Entanglement sounds like a way around the speed of light. Two particles linked so tightly that a change here seems to snap reality there instantly over any distance. Measure one spin here and you instantly know what the spin must be over there, even if there is on the other side of the galaxy. On the surface, that feels like a cheat code. Flip a bit in one lab, flip information in another lab faster than any radio signal could move. If that worked, the whole prison would crack. The problem is the universe is weirder than that and also more strict. Entanglement really does link outcomes, but not in a way you can steer. You don't get a hidden control knob. You get a shared randomness that only looks organized after the fact when you compare notes the slow way. This is where Bell's work in the 1960s comes in. John Bell asked a very direct question. Could these quantum correlations be explained by some hidden classical story, where the particles carry pre-agreed instructions and everything just looks spooky because you don't know those instructions? If that were true, you wouldn't need any local, non-local weirdness, just old-fashioned variables you haven't measured. Physicists set up tests, now called Bell tests, to push that idea hard. They made pairs of entangled particles, sent them to far-apart detectors, sometimes separated by kilometers, and chose measurement settings quickly and independently so that no light-speed signal could go from one detector to the other in time to coordinate the results. If there were local hidden variables, the statistics of the outcomes would follow a certain limit, the Bell inequality. Quantum mechanics predicted those limits would be violated. When the experiments ran, the data lined up with quantum mechanics, not with any simple local hidden variable theory. The correlations were too strong in the specific patterns that the quantum rules forecast. That result has been repeated over and over with better timing, better detectors, and with loopholes closed using fast random switches and careful shielding. The universe really does behave in a way that defies everyday locality and realism. Entangled particles aren't just two coins with preset sides. They act like parts of one shared state even when they're far apart. So at this point, it's tempting to say, fine, locality is broken. So why not use that to send a signal faster than light? This is where the no signaling rule wrecks your hopes. Here's the key point. When you measure your entangled particle, the result you get is random. You might call the outcomes up or down, or 0 and 1, but you do not get to choose which one appears. The quantum rules only give you probabilities, not control. That means you cannot encode a message in the choice of outcome, because you're not the one making that choice. You push the button, the detector clicks, you write down a random bit. Your partner, far away, measuring their half of the pair, also sees random bits. If you both measure in matched ways, your lists of bits will be correlated, but each list by itself just looks like noise. There is no pattern in your local data that says, the other person is sending this word or that number. To extract any meaningful information, you both have to later share your results over a normal, light-speed limited channel. Compare them, and then the hidden order pops out. The correlations are there, but they are only visible after you've done the slow communication. So entanglement does not let you send a signal faster than light. It lets you share a weird, non-local structure that looks spooky, but it refuses to give you any steering power over it. The universe gives you instant correlation, but locks it behind no controllable signaling. That's why physicists sometimes call the no signaling rule the real killjoy here. It saves causality and it keeps your prison intact. This is not just theory on paper. This has been pushed into real-world infrastructure.
We've sent entangled photons through optical fibers over distances of hundreds of kilometers. We've bounced entangled states between ground stations and satellites over thousands of kilometers. In those setups, you can test Bell inequalities on continental scales, and you can use the correlations to share cryptographic keys in a way that's secure against eavesdropping. If someone tries to measure or tamper with the entangled photons, they disturb the correlations and you can detect that. But notice what never happens in any of these quantum communication protocols. Nobody sends a usable bit of information faster than light. The entangled pairs give you shared randomness and security, not superlunar chat. Whenever actual human-readable information travels from one lab to another, it goes over classical channels, fiber links, radio, lasers, all obeying the same speed of light. The entanglement is the resource, but the message itself never outruns a photon's standard pace. So where does that leave you? Entanglement absolutely tells you the universe is deeply non-classical, that your common sense picture of separate objects with separate properties is wrong. It destroys the simple version of locality and realism you grew up with, but it does not open a hole in the causal structure. You cannot phone the Andromeda galaxy faster than light. You cannot trigger events in your own past. You cannot cheat the light cone. Even at the quantum level, the cosmos enforces the same light speed rule that holds rockets back and stretches conversations into decades. Quantum theory bends your intuition, but it doesn't bend the prison bars. The same ceiling sits on top of particles, fields, beams, and entangled states. So after looking at relativity, black holes, cosmic expansion, nature's highest energy particles, and quantum tricks, the pattern is brutally consistent. Every path you try hits the same wall. That raises one last question. If you can't change the speed of light, what if you could just change its value, live in a universe where the limit itself is different? Would that finally crack the cage, or would you just trade one prison for another, with different rules but the same hard boundaries on what's possible? Here's the part that really stings. The prison walls aren't static, they're actively closing in on what you can ever reach. The speed of light sets the ceiling, but something else is pushing more and more of the universe beyond that ceiling, and we gave it a very bland name: dark energy. In the late 1990s, two independent teams of astronomers were using Type 1a supernovae as distance markers. These are special exploding stars that, after you account for a few details, have roughly known intrinsic brightness. If you know how bright something really is, and you see how faint it looks, you can work out how far away it is. They expected those distant supernovae to fit a universe where expansion was slowing down under gravity. Farther objects should be dim, but not too dim. What they actually found was worse. The distant supernovae were dimmer than they should be in a slowing universe, meaning they were farther away than expected for their redshift. The only clean way to explain that was that the expansion of the universe isn't just ongoing, it's speeding up. Space isn't just stretching, it's stretching faster and faster. Instead of pretending we understand the underlying physics, we lump the cause into a term: dark energy. In the simplest picture, it's an extremely low but almost uniform energy density built into space itself. Every cubic meter of vacuum carries a tiny amount of this stuff, and when you add up that tiny amount over the vast volume of the universe, it dominates the large-scale dynamics. So if dark energy is really in charge, not gravity from matter, what kind of future does that actually give you? In a universe where dark energy dominates, the expansion rate doesn't just drift around. It tends toward a roughly constant value over long times. That leads to a very specific behavior. Distances between far apart, unbound objects grow in a way that's close to exponential. Take equal chunks of time, say every billion years, and the separation between two distant galaxies gets multiplied by some fixed factor each time. It doesn't just add a fixed amount of distance, it multiplies by a factor again and again. In plain language, anything not glued together by its own gravity will recede from us faster and faster as time goes on. It's not that its local speed through space violates light speed. Instead, the space in between keeps expanding so aggressively that the gap grows faster than any signal can close it. The cosmic event horizon you already heard about becomes a hard wall around our future. There's a radius beyond which anything that is outside right now will never receive any signal we send, and anything that is inside now but not bound will eventually cross that line and be gone for good. So, what actually stays with us in this picture, and what gets pulled away forever? On smaller scales, gravity still wins. Our local group of galaxies, the Milky Way, Andromeda, and a bunch of smaller galaxies, is gravitationally bound. The mutual gravity inside this group is stronger than the push of dark energy at that scale. Over tens of billions of years, these galaxies will interact and merge into a single giant galaxy, sometimes nicknamed Milkdromeda or something similar. That final object, plus a few tightly bound companions, will stick together. But more distant galaxy clusters, the big piles of hundreds or thousands of galaxies out beyond our local group, are not bound to us. Their own internal gravity keeps their members clumped, but the cluster as a whole is not tied to us. Over time, dark energy will push those clusters away faster than any light signal we send can catch up. Even if you fire a laser or launch a probe today, once they pass the evolving event horizon, there's no longer any causal path between us and them. Fast forward far enough, and the only thing left inside our future light cone, aside from local debris, is that single merged galaxy made from the local group. Everything else fades over the horizon, not just practically unreachable, but unreachable in principle. Our observable universe shrinks in a meaningful sense to one island. And before those distant galaxies are fully gone, the light they send us is being shredded by expansion. As the universe accelerates, photons traveling through it get stretched more and more. A galaxy that today shows up in visible light will, over billions of years, drift into the infrared, then into microwave, then into radio wavelengths so long and weak that no realistic detector can pick them out from background noise. So it's not just that the galaxies move out of reach. Their light itself is redshifted into oblivion. The photons we currently use to map the large-scale structure will be cooled and diluted until they effectively disappear from our sky. To any future observer, those galaxies won't just be far, they'll be gone from the record. There will be no practical way to even know they were ever there, unless someone left extremely careful notes. Roll the clock back mentally to the early universe, and then forward again to see the trend. Early on, everything was closer together. Gravity dominated over dark energy. Light, in principle, could crisscross big chunks of the universe, linking regions more tightly in terms of cause and effect. As time goes on and the universe expands, dark energy becomes more important relative to matter. The acceleration ramps up, the event horizon takes shape, and more of space-time slips outside anyone's future light cone. The speed of light sets the basic causal rule. No influence is faster than this. Dark energy weaponizes that rule by pushing huge regions of the universe beyond the distance where even light-speed signals can ever get through. The longer the universe exists, the smaller the fraction that any given observer can ever see, let alone reach. Early observers get to see a richer, more connected cosmos. Late observers are stuck in smaller and smaller islands, with most of reality locked permanently outside their horizon. So as time passes, the prison doesn't relax, it tightens. The walls defined by light cones and event horizons cut off more and more of what used to be in range. And if the large-scale structure of the universe itself is sealing you in, with the ceiling locked at light speed and the walls pushed by dark energy, there's one last desperate idea people reach for. Stop fighting as a massive object and try to become light itself. But even that fantasy runs right into the same hard rule. You are never going to become light. And the reason isn't mindset or technology, it's category. In the physics you actually live in, there are two kinds of particles, and you are made entirely from the massive kind, plus some force carriers. And there's no button that flips you from one club to the other.
So, the first hard truth is photons don't decide to go at light speed, and you don't choose to go slower. Those are structural facts about the kind of stuff you are made from. If you want to move at the speed of light in the strict sense, not almost, you would have to erase your rest mass or change the fields that give particles mass in the first place. In modern physics, mass comes from how particles interact with fields like the Higgs field. To turn you into something that actually moves at light speed, you'd have to rewrite the standard model of particle physics, not just bolt a better engine to a spaceship. Given the rules we actually measure, the pattern is fixed. As you accelerate a massive object, its speed creeps toward the speed of light, but each extra step takes more energy than the last. You pour in energy, your kinetic energy shoots up, your time dilation ramps up, your effective inertia increases, but your speed inches closer to the limit more and more slowly. Mathematically, the energy you need blows up as you approach light speed. Hitting the limit exactly would require infinite energy. Infinite is not a lot, it is never. That's the clean, abstract argument. But even long before you hit that abstract wall, reality starts attacking you in much more physical ways. Even cruising close to light speed is dangerous in a way that's easy to underestimate. The space between stars is not perfectly empty. There are a few atoms per cubic centimeter, bits of dust, stray particles, photons from the cosmic microwave background. At normal speeds, that gas is irrelevant. At a significant fraction of light speed, in your ship's frame, those atoms turn into high-energy bullets slamming into your hull at a huge fraction of light speed. Each impact dumps energy as heat and radiation. Your forward hull is getting hammered by particle beams you didn't ask for. The faster you go, the more violent each collision becomes. To keep human passengers alive, you need massive shielding, thick layers of material, maybe active fields to absorb or deflect that energy. But every kilogram of shielding is another kilogram you have to accelerate. The more you protect yourself, the heavier you get, and the harder it is to get closer to light speed without absurd amounts of energy. On top of that, if you try to reach these speeds in any reasonable time, you need serious acceleration. A comfortable acceleration for long periods is maybe 1 g, about 9.8 meters per second squared, Earth's gravity. Higher than that for long durations starts to crush human bodies, strain hearts, and wreck internal organs. Relativity does not magically make your chemistry light compatible. It just makes your proper time, your personal clock, slow down relative to distant observers when you move fast. From your own point of view, your body still runs at normal speed. You don't feel like light. You don't turn into a photon. You stay a slow, fragile chemical process riding in a metal box, trying not to get fried by radiation and debris. So in practice, even almost light speed is already at war with both hardware and biology. And that's assuming you stay flesh and blood. What if you give up on that and go full sci-fi? Upload your mind and send it as data. Say you somehow scan your brain, convert your mental state into digital information, and store it in a computer. Now you're a big file, so you decide to transmit that file instead of your body. You send it down a fiber optic cable or broadcast it with radio waves to a receiver somewhere else. That sounds like a shortcut, but the same limit quietly sits underneath it. Bits in a fiber optic cable are carried by photons moving through glass. Light in glass travels slower than in a vacuum, maybe around 200,000 kilometers per second instead of 300,000. Radio waves in space are electromagnetic waves in a vacuum. They move at the same speed as light. Either way, your upload itself is now constrained by the velocity of photons or electrons in a medium that still obeys the speed of light limit. So whether you're made of meat or made of bits, whether you're writing in a starship or encoded in a beam, you do not outrun the fundamental speed built into space-time. You can change the format, you can change the substrate, you can't change the ceiling. At this point, you'd hit the same wall from every angle. Classical motion, rockets, relativity, quantum tricks, biology, information.
The natural last move is to try something more radical, not break the limit, but move to a universe where the limit itself is different. If the speed of light were much slower or much faster, would that finally unlock things, or would you just find yourself in a different kind of cage, with different rules but the same hard boundaries on what can exist and what can connect? You're not just stuck with a speed limit, you're stuck with this specific speed limit. Change that number and you don't get freedom, you probably lose the kind of universe you need to exist in the first place. Take a very simple tweak. Say the speed of light was 10 times lower, 30,000 kilometers per second instead of 300,000, about 18,600 miles per second instead of 186,000. That sounds like a minor adjustment, a tighter ceiling, maybe more annoying delays. But C doesn't just set how fast light moves, it's wired into electromagnetism, into how atoms hold together, into how radiation and matter interact, into how stars burn. Those forces all show up together in the equations. Many physical models suggest that if you push the speed of light down by a big factor without changing anything else, you don't just get slow light, you risk breaking the balance that gives you stable atoms and long-lived stars. Energy scale shift, interaction strength shift, and the structures you rely on might not form or be unstable on short timescales. You could end up with a universe where atoms fall apart too easily, or where stars explode or fizzle out almost immediately. Even if you ignore all that and pretend atoms still work, communication delay on everyday scales would blow up. On a planet with Earth size, it's about 40,000 kilometers around the equator, roughly 25,000 miles. At our current light speed, a signal wraps around in a fraction of a second. Drop light speed to 30,000 kilometers per second, and suddenly even crossing a planet becomes slow enough that you'd notice lag in ordinary life. High-speed networks would have built-in delays of fractions of a second or seconds just to cross continents. On interplanetary scales, the delays that already annoy space engineers would become long enough to completely crush any sense of control. So slowing light doesn't look like same universe worse speed, it looks like maybe no universe that can support you at all, and if it does, everything feels even laggier than it already is. The next move is obvious. Push the speed limit up. If the speed of light were 10 times higher, 3 million kilometers per second instead of 300,000, about 1.86 million miles per second instead of 186,000, that sounds like breathing room. Messages and ships can go faster, horizons move outward, the prison stretches. But again, you can't just tweak that one number in isolation and expect the rest of physics to politely stay the same. The speed of light shows up in relativity, in electromagnetism, in quantum field theory, everywhere. Crank it up without retuning the rest, and you change how strong forces appear, how radiation behaves, how quickly energy moves around. Stars balance gravity pulling in against pressure from nuclear reactions pushing out. That balance depends on the rates of reactions and on how energy is transported, which are both tied to fundamental constants, including C. If you jump light speed up by a big factor without changing anything else, you might end up with stars that burn their fuel much faster and die young, or with nuclear reactions that proceed in different channels and blow apart forming structures before they stabilize. You could very easily get a universe where complexity doesn't have time to form before everything runs out of fuel or collapses into simpler states. Push even harder, and you might leave the regime where matter forms the kind of bound states you need for chemistry. The details depend on how all the other constants move, but the core point is simple. Light speed is embedded in a web of relationships. Change it, and you don't just stretch the prison, you risk tearing down the building. So the real lever is not light speed alone. It's the combinations of constants that set the scale of interactions. That's where dimensionless numbers come in, and those are what actually decide whether a universe can make atoms and life at all. One of the key dimensionless constants in physics is the fine structure constant. It's roughly equal to 1 divided by 137. That number controls how strongly light and charged particles interact, how electrons sit in atoms, how spectra look, and a lot more. It's built out of several fundamental constants combined, including the speed of light, the elementary charge, and Planck's constant, arranged so that the units cancel and you're left with a pure number.
What really matters for structure is that pure number, not the individual constants floating independently. If you change the speed of light without changing the others in a very specific way, you change the fine structure constant. That means you change atom sizes, bond strengths, how easily electrons jump between levels, and how chemical reactions unfold. A small shift might already give you a universe with very different chemistry. A bigger shift could give you no stable atoms, like the ones you know at all. So just make light faster or just make it slower is not a clean option. You'd have to retune an entire network of constants to keep a universe that even vaguely looks like one where stars, planets, and life can exist. And once you do that, you probably end up back in a regime where in some units, there is still a hard causal speed limit, and still a huge gap between that limit and what any local process can actually use. And this is where an anthropic angle shows up, not as philosophy, but as a selection effect. You exist in a universe where the constants, including the speed of light and those dimensionless combinations, fall into a narrow window that allows stable atoms, long-lived stars, and complex chemistry. That same speed limit that ruins your dreams of hopping between galaxies is part of the structure that lets galaxies form in the first place, that lets stars burn steadily for billions of years, that lets planets sit in habitable zones for long enough that biology can evolve. In that sense, your prison is also your support structure. The same rules that cage you also hold everything up. Break the bars, and you probably bring the ceiling down with them. A universe with no strict causal limit might be full of paradoxes or unstable physics. A universe with very different constants might not build the kind of layered, long-running structures that you need to think, complain about speed limits, or design rockets. You're stuck in this parameter set partly because outside of it, there may be nothing like you at all. Even if there are other universes out there in some larger multiverse with different constants and different speed limits, you don't have access to them. There is zero experimental evidence of any mechanism that lets you jump between such universes, send signals across, or even confirm their existence directly. From your standpoint, they are not options. They are at best mathematical possibilities you can't reach. So you are locked into a light speed limited universe, and into this particular version of that universe, with this specific balance of forces and constants. The bars aren't just a local rule you might outsmart, they are built into the only physical reality you ever touch. Which leads to the last uncomfortable rearrangement of the whole picture. If you can't break the prison and you can't swap it for another one, you have to ask a different question. What is this speed of light actually telling you? Is it really about how fast light goes, or is it something deeper? The basic conversion between space and time that defines what cause, effect, and even your story mean at all. So after all this, calling it the speed of light is almost the wrong name. It makes you think of how fast a thing moves, when the real point is, this number is the structure of reality. It's not just a big speed, it's the conversion rate between space and time, the tilt of your light cones, the hard ceiling on how quickly a cause can produce an effect anywhere in the universe. In the equations of relativity, this constant plays the same kind of role that 90 degrees plays in geometry. It defines what straight, right, and even possible mean. Change it and you don't just get faster messages, you get a different space-time. Once you think of it that way, the next question is brutal and simple. What breaks if you remove the prison and let signals move arbitrarily fast? If you could send information at any speed you want, you could set up chains of events that loop back and hit their own starting points. Relativity tells you different observers moving at different speeds slice space-time into now and later in different ways. If faster-than-light signals existed, in one frame you send a message forward in time. In another frame, the same message can look like it went backward in time. With a clever enough setup, you could send a warning into your own past. Don't press that button, then choose to obey it or ignore it, and you're straight into paradox territory. You get scenarios where an event prevents itself from happening or causes itself to happen, and there is no way to assign a single consistent timeline that includes all of those steps. Cause and effect stop being well defined.
Physics becomes a choose-your-own-adventure book with no consistent ending. By enforcing the rule, no signal outruns light, space-time cuts off all of those loops. Light cones exist precisely to separate can influence, could have influenced, and never connected. And that separation is what keeps timelines from folding back on themselves. So the same wall that frustrates you when you try to talk to another star is also the wall that stops your future from reaching back and punching your past in the face. No prison, no causality. There's another layer to this, less flashy but just as important. The same limit that blocks super fast messages also forces particles, fields, and forces to play by the same rules everywhere. A photon emitted in a lab on Earth and a photon emitted in a galaxy 10 billion light years away move at the same speed and vacuum. They transform the same way when you change frames. They fit into the same equations with the same constants sitting in the same place. That sameness is why physics works as a universal language. You can measure the spectrum of hydrogen in a nebula on the other side of the Milky Way and compare it to hydrogen in a discharge tube in your lab, and they match. You can write down the laws of electromagnetism or relativity on Earth, and they correctly predict the behavior of light from quasars billions of light years away. The bars that stop anything from going faster than light are the same bars that force a photon to behave identically wherever and whenever it appears. If that weren't true, you'd be in real trouble. If different regions could have different maximum speeds, or if signals could slip outside their light cones here but not there, you couldn't trust that any experiment you do locally says anything about the wider universe. There would be no reason to believe your equations hold beyond your own neighborhood. The whole project of cosmology would collapse. The bars keep the rules universal. Zoom back down to your level, because this is where it gets personal. Given all of this structure, what do you actually get to have? You get one finite chunk of space-time, one past light cone, full of signals that have had time to reach you, and one future light cone, full of events you can, in principle, influence. Inside that region, you can think, build cities, send probes, record data, ruin things, fix things. Every relationship you have, every memory, every measurement lives inside that causal bubble. Outside it, most of the universe will never even know you existed. It doesn't matter how advanced your technology becomes. You can't send a signal into a region of space-time that is space-like separated from you. You can't reach across an event horizon. You can't influence galaxies already beyond the cosmic horizon pushed by dark energy. The boundary drawn by light speed and the expansion of space is also the boundary of your story. And that's true for every other observer too. Each one lives in their own light cone island with a past they can, in principle, learn about, and a future they can, in principle, affect, and almost everything else forever out of play. So here's the final twist that ties the whole thing together. On cosmic scales, the speed of light is absolutely not fast. It strands you in one galaxy. It makes crossing the Milky Way 100,000 years even for light. It turns interstellar conversation into centuries of waiting. It lets dark energy erase most galaxies from your future. It is a prison in every straightforward sense. But the same speed limit gives you a consistent timeline where causes come before effects, and paradoxes don't rip logic apart. It gives you stable matter, because the same constant appears in the laws that hold atoms and fields together. It gives you universal physics, the ability to do experiments here and trust they apply everywhere. It gives stars lifetimes long enough, billions of years, for planets to cool, chemistry to run, and life to evolve nervous systems that can complain about speed limits on a YouTube video. Take away the prison and you don't get more access. You probably lose the entire kind of universe that lets you exist and ask these questions at all. The limit that blocks your path to the rest of the cosmos is the same limit that makes a coherent cosmos with reliable laws and long-lived structure possible in the first place. So yes, the speed of light is a cage. It locks you into a tiny sliver of space-time and cuts you off from most of what exists. But it's also the steel frame holding reality together. You are not just trapped by C, you are defined by C. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.